welcome to week 7 of the vibration course. We're going to be talking about instruments for vibration detection and analysis. So the logic, the logical progression here is kind of maintenance strategies and how we can use vibration. Then we looked at some of the things that vibration can pick up. We looked at all the characteristics of vibration, and we talked about the units and ways of measuring those characteristics with different units: acceleration, displacement, and velocity. And then we looked at how to analyze it a little bit with using two different types of data sets. One is the time waveform, and the other one was the vibration signature, aka the FFT, aka spectrum analysis. So we kind of covered all that off. Now the next part that's kind of really critical before we actually go and start taking these vibration measurements is to look at the actual hardware. Talk about the actual hardware and how it works, because an understanding of that is going to be really helpful when you're actually deciding on where to mount instruments, and when you're getting maybe some changes in troubleshooting the differences in a trend or reading. Maybe you have a measurement drop off in amplitude and you're not sure why. Understanding some of the equipment can really be important in that. So not too long ago, there was a few different types of detection devices. There was these kind of simple single button vibration meters that were handheld, where you just simply would just hold down the button and it would give you a readout in peak velocity and or vibration severity, and then you just document that and note it down. It was very kind of crude and very simple, but as long as you had a little bit of understanding of vibration, you could, without getting too involved with a lot of the computer software and things that were around at the time, you could get, in general, a good idea of the overall severity of the vibration of a machine as it was aging and going through the year after year of operation. As time kind of progressed on, they moved towards away from these vibration meters to what they call vibration frequency analyzers, or your data collectors, which is what we're going to be working on in the shop. And that's really kind of like the all-in-one kind of computer, where they're going to take the vibration readings from the transducer, and it's going to do all the calculations, and it gives you a real-time readout of what you're looking at. You can look at the time waveform, you can look at the FFT, you can look at the trends, you can signal alarms, and do a lot more information with it than just these kind of simple machines of press a button and hold a button. So I want to talk about a vibration transducer and accelerometer, what the differences are, and but basically, regardless of whatever vibration instrument you're being used, the kind of the heart of each and every instrument is the vibration transducer. So this is the device that's held or attached to the machine to convert the machine's mechanical vibration into an electrical signal that can be processed by the instrument, or into like a measurable characteristic of vibration, amplitude, frequency, and the phase of it. Many different varieties of these vibration transducers have been used over the years, but with few exceptions, the transducer provided as standard when you buy these units of all the present day vibration meters, analyzers, and data collectors is definitely the vibration accelerometer. So a vibration accelerometer is a type of vibration transducer. There's a few different other ones that are out there. There's velocity sensors, there's proximity sensors, and then there's accelerometers. So the three ones. So we're going to talk mostly just about the vibration accelerometer and how that works. So an accelerometer is a self-generating device that produces a voltage output proportional to vibration acceleration. So if we have a doubling of acceleration, we get a proportional increase in the voltage that's being generated by the accelerometer. The amount of voltage generated per unit of vibration acceleration, which if you remember back to the units that we use to measure acceleration, it's a G. So the unit of vibration acceleration is called the sensitivity of the accelerometer and is normally expressed in millivolts per G. Okay, so 1 millivolt equals but 1,000th of a volt. Accelerometers are available with sensitivities ranging from 1 millivolt per G to 10,000 millivolts per G, depending on what the application that you need. However, most accelerometers for the general kind of purpose vibration detection are somewhere in the range of 10 to 100 millivolt per G. And we're going to talk about kind of the significance of the sensitivity a little bit later in this discussion. So what we have here in this diagram is a very simplified version, a simplified diagram of a typical accelerometer and how it's constructed. The component of the accelerometer that generates the electrical signal is something called a piezoelectric element. A piezoelectric material is a non-conducting crystal that generates an electrical charge when mechanically stressed or squeezed. The greater the applied stress or force, the greater the generated electrical charge. So, if you ever use one of those push button starts on your propane barbecue, or use like one of those barbecue lighters with the long piece where you click and it creates a spark to ignite a fuel. That's really what, in essence, what the piezoelectric crystal is. I'll add a video in the content section if you want to dive a little bit more into what the piezoelectric elements and how they work. But basically, it's a crystal that the more you squeeze it, the more voltage you get across the two leads. The more you get, it's an indication, that proportional indication of how much acceleration or how much force that you're getting there. So getting back to this, many natural and man-made crystals have piezoelectric properties. There can also be a number of ceramic materials that have the same electrical properties by the addition of certain impurities and by suitable processes. And these are called ferroelectric materials. Most commercially available accelerometers used today incorporate ferroelectrical materials because they can be fabricated in a variety of shapes, and their piezoelectric properties can be controlled more easily than crystals to suit many applications. So when we talk about crystals, we're mainly talking about something like quartz, where you would have to take the actual raw element of a quartz crystal and manufacture it to suit this application. They can do the same thing with a simulated material, these ferroelectric materials, where the piezoelectric, you don't have to necessarily use the crystals. It's a little bit more expensive to make it that way, but they can do it under kind of lab conditions to create the exact type of resolution for recording that they need. So again, looking back at this diagram here, the accelerometer consists of a mass. So this mass is kind of this top piece here. It's usually made out of stainless steel and is compressed against a stack of these piezoelectric discs. The size and number of the discs used in the accelerometer determines not only its sensitivity but its usable frequency range. So when an accelerometer is held or attached to a vibrating object, the piezoelectric elements will be subjected to resultant inertia forces of the mass. So basically, the mass wants to stay put, and then the accelerometer is mounted on the bearing cap or whatever. So when the mass wants to stay because of inertia, and then there's a physical push on the mount of the accelerometer, that squeezes on those crystals, and it gives you an electrical charge signal proportional to that acceleration. So the operation of an accelerometer used for the measuring and analyzing machinery is exactly the same as that of a ceramic cartridge used on things like record players, where the vibration of the needle riding in the grooves of the record is kind of converted to an electrical signal. So the amount of electrical signal generated by the piezoelectric element is relatively small, and many times it has to be transmitted to by an interconnected cable to the vibration instrument or analyzer, and there may be some distance away. So we have to have an amplifier directly inside the accelerometer also to amplify that signal. So if we have to transmit some of these signals through long cables, some of these accelerometers are just permanently mounted on the equipment, and they have a long lead that runs to the data collector somewhere. So they have an actual amplifier in there that increases the electrical signal. Using those accelerometers with the built-in amplifiers can pretty much get us the ability to connect with cables of 1,000 feet in length or longer without any kind of real noticeable signal loss or any kind of interference. So what about displacement, velocity, and some of the spike energy measurements that we talked about? We talked these accelerometers obviously can pick up acceleration, but what about some of these other ones? So pretty much, although the vibration accelerator generates an electrical signal proportional to vibration acceleration, or G's, it's really easy to convert this electrical signal to the other parameters, such as vibration amplitude of velocity and displacement amplitudes. So this conversion from acceleration to velocity displacement is performed electronically as within the data collector, the device. It's just really a math equation that is doing in real time. Converting the acceleration signal to velocity is called single integration, and converting the acceleration signal to displacement is called double integration. Of course, spike energy is simply an acceleration signal that has been specially conditioned with that band pass filter we talked about between 5,000 hertz and 50,000 hertz, and true peak-to-peak circuitry instead of the root mean square responding circuitry. But that's just like kind of not super critical important stuff to know. Just that you're taking the acceleration measurement and you're converting it through a single integration calculation to velocity, and then you can take the acceleration and turn a double integration to turn it into displacement. So it's like a two formulas. So at the end of the day, the accelerometer transducer can be used to obtain measurements of all vibration parameters: the displacement, velocity, acceleration, and again those spike energy, ultrasonic frequencies that we talked about last week. So that's kind of like why it's the preferred vibration transducer, because it can detect all of the things that we've been talking about. However, there's a bit of a concern for anyone involved with the predictive maintenance program involving vibration detection and analysis. It's whether the vibration instrumentation is capable of detecting all the problem-related vibration frequencies that can be generated by their machines. So in this construction here, the number of disks and the construction depending on how many discs and how it's made, can pick up only certain types of frequencies. So accelerometers in general are classified as low frequency, general purpose, and high frequency accelerometers. So general purpose, low frequency, high frequency, and then there's some permanently mounted ones. So when we look at this chart, the general purpose accelerometers will normally accommodate the vibration frequencies ranging from 120 cycles per minute, so 120 RPM, to 60,000 CPM. So of course these specifications are typical and would definitely vary depending on the specific manufacturer or the model number. But unless otherwise specified, most portable vibration meters, vibration data collectors, analyzers are supplied with a general purpose accelerometer. And that, in fact, will cover the vast majority of vibration detection and analysis requirements. That's great. Permanently mounted accelerometers are basically general purpose accelerometers designed for low cost installation. So when you actually have to go and mount these things in place, they're kind of just like a less robust version of doing the same thing that you would clamp or adhesively mount to the machine and just leave in place the full time. The accelerometers that come with the machines are quite expensive. So if you have to just mount them all over the place, it would get quite expensive. They can get damaged, so they just have permanently mounted ones. General purpose accelerometers cover like a fairly wide range of the problems related to vibration frequencies that are probably suitable for the vast majority of machinery vibration detection and analysis applications. However, there are some problems that can result in vibration frequencies well below the range of a general purpose accelerometer. Like examples would be like some machines like extruders or mine hoists or mixers and agitators. They often can run at speeds below 100 RPM. In addition, on paper machines, various rolls may have operating speeds well below 100 RPM with the felt speeds below 20 RPM. So for these applications, these low frequency accelerometers are definitely required when things are turning slowly. So looking at our chart here, the low frequency accelerometers can detect vibration frequencies as low as 6 CPM, so 6 cycles per minute, so like one revolution every 10 seconds or so. But I got to remember that this is typical of low frequency accelerometers currently available, and might not, or it might vary depending on the kind of specific accelerometer manufacturer, the model number, how recent it's been made. So just be sure to check the accelerometer specs for the exact recommended usable frequency range. And although these low frequency accelerometers are designed to detect very low vibration frequencies, it can be seen on the chart here that these low frequency can be used for fairly high frequencies as well. So typically up to 60,000 CPM. So this is a pretty usable frequency range. It covers most of the normal vibration problems encountered on general machines like motors, pumps, fans, and generators, etc. It's suggested that these low frequency accelerometers not be used for general purpose applications. In order to accurately detect very low frequencies of vibration without interference from other noise sources such as radio frequencies or high voltage magnetic induction low frequency accelerometers, they have to have high sensitivities. So in other words, these low frequency accelerometer must generate high levels of electrical signal when subjected to vibration. So from the chart, it can be seen that these low frequency accelerometers can typically have sensitivities up to 10,000 millivolts per G, which is extremely high. And although such high sensitivities are needed for successive low frequency vibration measurement, this also makes the accelerometer susceptible to damage if it's dropped or handled roughly. So they're quite fragile. And simply dropping one of these on a route with this high sensitivity can result in damage to the amplifier or the materials inside. So they have to be handled really carefully and to avoid damage. They're very sensitive instruments. So I guess what I'm trying to say there is that even though those low frequency accelerometers can be used, they're highly specialized very fragile equipment. So you don't often use it. You'd still want to stick with your general purpose, even though the low frequency ones could work. Those ones are specifically for the low RPM. On the other end of the spectrum, some machinery problems can generate vibration frequencies that are well above the usable range of a general purpose accelerometers. So let's look at kind of an example of that. This would be an example of a high-speed multi-stage gear-driven centrifugal compressor. In this case, a fundamental gear mesh frequency can be calculated by taking the number of teeth on that bull gear, which is 344, and times it by 3,580 RPM, and you can get a gear mesh frequency of 1,231,000, which is incredibly high for our CPM for the vibration reading. Obviously, this vibration frequency is way above the usable frequency range of our general purpose accelerometer. So in this case, we would need to use a high frequency accelerometer. So let's talk about the accelerometer mounting. So we talked there's different types of accelerometers. There's the low frequency, high frequency, general purpose, but there's also really important and probably the most relevant part of this whole thing. Like if you're just getting started in this, you're going to have a general purpose. You're going to have all the data collectors and stuff set up. You'll have your route set up, but it's the mounting. It's the going around and actually measuring. So regardless of the usable frequency range of the accelerometer, whether or not the high frequencies of vibration can be detected, and a lot of it depends entirely on how the accelerometer is mounted. So these pictures are the four most common methods of mounting or applying an accelerometer to a machine to take readings. And typical usable frequency ranges for each mounting technique is going to be summarized here. The best way to mount an accelerometer is the stud mounting. This provides the maximum usable frequency range and is especially recommended for high frequency accelerometers. So for best results, the machine surface should be flat, smooth, and free of paint or dirt. For maximum bonding, a layer of silicone grease should be applied to fill any tiny imperfections between the mating surfaces. And also make certain that the threaded stud is not too long. If the stud is too long and it bottoms out in the tapped hole inside of that accelerometer housing, the usable frequency range is greatly reduced. So be sure it's not loose. Tighten torque to approximately 30 to 50 inch-pounds, and don't over torque these studs, because you can actually damage and distort what's inside of there. But yeah, stud mounting is definitely the best, and it's for especially for high frequency range. Adhesive mounting although it's not really as good as stud mounting, it can provide very good frequency response, as almost as good as the stud mounting. There's also machines the machine surface is the same way. It has to be flat and smooth and clean, and you have to grind all the paint off to give a secure bond for the adhesive. The layer of adhesive when you glue these down should be as thin as possible. You don't want to be it can dampen some of the vibration signal and reduce the amount of frequencies that we can pick up. The magnetic holder, while stud mounting and adhesive bonding provide excellent frequency response, these magnetic holders mount may not be like the gluing and the studs are not practical for routine vibration checks. There's a large number of machines and the measurement points that have to be involved in these programs. So where the stutter adhesive mounting is not practical, the use of a magnetic holder is the next preferred mounting method. The maximum frequency response, a layer of silicone grease, you just smear that on there before you would mount the accelerometer magnet. Of course, the surfaces have to be clean and free of paint, and if the poles or surface of the magnet has been nicked because of like rough handling, or maybe you dropped it, I got to make sure that those nicks are carefully removed to make sure that this thing gets is installed solidly. When using these two poles, so you see these two magnets here, and we'll work on this a little bit in the shop. We'll go and take some readings. When using the two pole magnets or regular rounded surfaces, make sure that the magnet is not rocking on the machine surface. If the magnet is rocking, this will not only reduce the maximum frequency range, but it's also going to introduce vibration frequency characteristics indicating like a looseness. So by far the worst is way to take these vibration readings is with a extension probe. Studies have shown that these extension probes tend to act like a mechanical filter and essentially eliminate vibration frequencies above about 60,000 CPM, which you can see inside of this chart here, that they have their own natural frequency that can really affect the readings. So the probe and because of probe resonance, really they're more or less done away with on any kind of critical vibration. So we just don't really use them too much anymore. They have some small reasons to be used, but they're not the best. The best would be, and the most common is going to be your magnetic. So when you're taking these readings, there's a need to be consistent. So making sure that you're taking the readings in the same spot every time, and that you're making sure that the machine is clean and free of paint and dirt and all that stuff. It's all really critically important. Since vibration forces generated by rotating components of a machine are passed through the bearings, vibration readings for both detection and analysis should be taken directly on the bearings whenever possible. So here's some pictures of some of these locations that you'd want to, and there's an X on the arrows where some of these are bad locations. Really, the way that you want to take these readings is pictured down below, where you would want to mount and take the readings on direct locations, like just directly on the bearing itself, like right here. This is saying like not on the housing, but directly right on the housing of the bearing as it sticks out. Ideally, all vibration readings taken on a horizontal and vertical direction should be taken directly on or as close as possible to the bearings, with the accelerator pointed towards the center line of the shaft. So you don't want it kind of pointing off. You want it to be directly. That's where you're going to get the best. Kind of almost like when you mount a dial indicator on something, you want it to be perpendicular to the surface. Axial vibration readings, we want to definitely take these on the bearings as close to the shaft as possible, but without compromising your safety. You really don't want to get too close to some of this equipment. You don't want to have any kind of jewelry or anything on, and you want to have your sleeves rolled up if you're going to be mounting any kind of accelerometer in around rotating equipment. A few more points here before we wrap this up, but vibration measurements should not be taken on thin structural members like fan housings, ductwork, or thin steel panels to evaluate the machinery condition. These components, because of their flexibility, may reveal really high amplitudes of vibration even though the machine's totally fine and running satisfactory. So small to medium-sized motors will have like a thin cast or steel shroud to guard the cooling fan. Vibration readings should not be taken on this guard. Radial measurements should be taken directly on the rigid motor frame as close to the outboard bearing as possible. axial readings can be taken on one of the bolts securing the fan shroud to the motor frame. As an alternative, axial readings may be taken on the motor feet. However, it should be noticed that these readings will normally be a lot lower in amplitude because of the fact that they're bolted to the base or the frame. Also, although it's recommended that vibration measurements are taken directly on the bearings of the machine, many times the configuration of the machine dictates where readings can be taken, and many times where readings can be taken is considerably less than ideal. In any case, the key to the successful predictive maintenance program is in the consistency of how you're taking the measurements. Even if it's not taking the most accurate measurement, as long as you're taking it in the exact same way, you can still compare the data week over week and trend and look at it. And you can also kind of use a little bit of your own experience based on some of the severity charts and alarms and stuff to kind of indicate whether or not what you're measuring is good or not. So even though some of these measurement locations may not be ideal places to take data, it's a significant increase in vibration is detected. A developing problem is probably the reason, and detailed analysis should be carried out to determine the cause if that's something that you find. Okay, so that's all about accelerometers and accelerometer transducers, how they work, where to take the readings, the different types of mounting. There's different ratings. Low frequency, high frequency, general purpose, and that's pretty much it for week 7. Next week we're going to look at vibration, at the actual analyzers, how they analyze a signal, and some of the data that they collect, and then some of the spectral analysis and some of the types of filters that they put on the data for identifying and kind of isolating some of these signals.